In this section, we're going to discuss searching, but more than that, we're going to discuss something called algorithm analysis and Big O notation. A linear search is the name given to a type of searching where we have a container, like an array, and we start at one end and we sequentially iterate over each element, checking to see if that element is the one we're looking for. We would start at index 0, go to 1, 2, all the way to maximum index. And if we find the element, we say the search was successful. Otherwise, we say it was unsuccessful, that we didn't find the element. In the best case scenario, the first element we search would be the one we're looking for. So that would be very fast. We would have this big array, we find it first try. That always feels good. Worst case is we search every element of the array and we don't find the information. We search n times, where n is the number of elements. The average is that we search the number of elements over 2, about half. If we were doing repeated searches, we on average find them in half the number of elements. This idea of worst case scenarios, best case scenarios brings up a topic called algorithm analysis. Computer scientists care very much about performance of algorithms because some of them take longer than others. A linear type problem is one where if we have n elements, the time taken to find or process those elements is proportional to n. N is small, the overall time is small. If n is huge, the overall time is huge. It follows a linear proportion. Even though we may have two different algorithms, A1 and A2, that work somewhat differently, still, if each one is sensitive to the number of elements, then we say they're both linear. Here I say assume three numbers, KLM, that represent different numbers of elements, where K is always less than L, which is always less than M. We would say the running time, T1, where we're processing K elements, T1, where we're processing L elements and M elements, is always going to maintain this order. The algorithm running with fewer elements is always going to complete faster than the one running with the medium number of elements, which is always going to run faster than one with a large number of elements. Even though A2 would have a different set of times, still A2 would be proportional to the number of elements. This proportionality is what brings us to Big O notation. Since these algorithms both depend on the number of elements, even though their actual runtime may be different, they're considered to be in the same family of algorithms. Big O notation is a funny concept because most of us are very computational minded. When working with Big O notation, we discover that when something's divided by 2 or multiplied by 5 or something, we ignore those things and just look for the largest single point of cost, and we describe algorithms in a family based on that. In linear algorithms, we say Big O is on order of n. So it's that proportionality based on the number of elements. Most linear algorithms are easy to understand and easy to implement. To make things faster than Big O n, we have to fundamentally change our approach. One such approach is called divide and conquer. It means to divide the data into multiple parts, often 2 parts, and work on half the data. And in the case of a binary search, what we do is we divide the data in half and decide, is the element we're looking for in the left half or the right half? And then we choose the half that it's in. We divide that in half and we decide, is it in the left half or the right half? And we keep dividing by 2, which means we're no longer working in linear time because we're eliminating most of the data. We're now working in logarithmic time, which is a lot faster. The algorithm, however, is more complicated than any linear algorithm. The binary search works by dividing the data in roughly half parts and keep doing that. For example here, let's say we had about 1 million data elements to search. A linear search would take on average about 500,000 searches to find one element. That's rather heavy expense. A binary search, on the other hand, would take about 20 searches. Now that's a vast improvement. But again, the binary search is a little more complicated to understand and a little more complicated to implement. The benefit of doing so vastly outweighs the extra complexity of the algorithm. One caveat, binary searches work only when data is sorted.